So we have the transpose of matrices here, and what we're going to do is go through what we mean by the transpose of matrix. So the transpose of A being an n by m matrix, that is n number of rows and an m number of columns, is a matrix we get when we write all the rows of A as the columns and then the columns of A as rows. What this means is that this is an example. If I have a matrix A given in this format, then all the entries I get in the column 1, I'm going to write them as my row 1 in a new matrix like this. I'm going to get that. So I have 2, 4, 6 in a row form, and I write the next column entries as row form like this. Okay, so when I write all of them, all the columns as a row, and put everything in a matrix form, then this is the transpose of A. And one thing is that when you transpose a matrix, each row, number of rows you get in the number of rows you had in the original matrix changes to become number of columns you get. What I mean is, in this A, the dimension of A is 3 by 2. We have 3 rows and 2 columns, but A transpose becomes 2 rows and then 3 columns. So you have a 2 by 3. Now in a B, we have a 3 by 1 matrix. If I transpose this, I'm going to get everything I have in the column 1, which is the only column we have, as a row, and this is going to give me a 1 by 3 matrix because I have 1, 2, 3 columns, but then I have only 1 row. An example that you can do very quickly here is that if I have C to be 1, 2, 3, 4, then the transpose of C is going to be writing all these as the first row and then writing these as the second row. But this is a square matrix, so when you transpose it, you still have the same dimensions, right? So what I'm going to do is I'm going to go through some properties of transposition of matrices and how to prove them, okay? So the first thing is that properties of, the first property is that A transpose transpose is equal to A. And I want to write a proof for this. Now, before anything, I want you to just look at this very quickly. If you look at a matrix A, or maybe let me pick the matrix C, which is 1, 2, 3, 4. The A11 entry is this one, right? So A11 entry is that. I have A12 entry to be 2. A11 entry is that 1, and then A21. All these things, what they mean is the row 2, the first value stands for the row. So row 2 column 1 is this 3, and then row 2 column 2 is 4, right? So A22 is 4. Or maybe C, I'm so sorry, I used A, but what I meant to write was supposed to be C11 and the rest, okay? Sorry. So if you would want to do that, you can actually do that. So C11 is 1, C12 is 2, C21 is 3, and then C22 is equal to 4. Now let's look at the transposition of C. What happened? Now the C transpose 1 entry is 1, still 1. But C transpose 1 2 entry is 3. What is the relation between these? You realize that they are the same. C21 and C12 transpose, they are having the same thing. What it means is that if you transpose a matrix and you had the little entry to maybe Aij, then A transpose is going to be Aji, right? What this means was, when I had a C21, right, and I transpose this, that gave me a C12, and that C12 is the transpose of it, and that gave me this, right, 3. So you realize that if I interchange just this 1 and 2, I'm going to get the same value. So C21 is equal to C12, or maybe, yeah, C12 transpose, right? So that's what it means. So I'm just going to change the I and J column, the row and then the column values. So if I have A, I'm writing a proof to this. So if I let my matrix A to be the square matrix of little Aij, okay, where these are the entries. So it depends on where your I and then J ends, okay. Now A transpose per our observation is going to be the transpose of Aij, and that's going to be Aji. So you're going to change the I and J position. Now I want to find the transpose of A transpose again, and that's going to be the transpose of this guy, because A transpose gave us little, so this is supposed to be a square bracket Ji, then transpose, and that's going to be interchanging I and J. So I'm going to have square bracket, then interchanging I and J, and this is the same as A. So that ends this proof, right? So that's a proof to why A transpose is equal to A. I hope this makes sense. So now let's go to the next one. If you have a constant K, so where K is non-zero constant, okay, you can actually look at zero constant, but I'm particularly interested in non-zero constant. Then Ka transpose is equal to K. I mean, when you transpose everything like that, you're gonna get a constant back, and then you transpose of A. So I have A to be that. Then Ka is gonna be K multiplying every entry. So every little Aij you get, you multiply that by K, right? And so Ka and transpose is going to be the transposition of Aij, right? So I'm going to have transpose, and K is a constant, so I'm just going to change Kji, right? So what this is going to happen is that I can factor K out, because K is multiplying everything I have, Aji. And if you look at this very carefully, this is the same thing as a transpose of A, because if I transpose A transpose in terms of this is going to be Aji. Okay, so this guy is going to be Ka transpose, and that ends the proof. So that's the proof to why Ka transpose is equal to K times A transpose. Now the next proof is that if I have A plus B, then I transpose all of them, I'm going to get A transpose plus B transpose, and that follows from the proofs I've been doing. If A and B are like that, then A plus B would be the little I, or maybe little I Aij plus this guy Bij. And I can say that I'm going to write this as square bracket of Aij plus Bij. Now A plus B transpose is going to be the transpose of Aij plus Bij. And like I said, the transpose is just interchanging J and I components. Okay, and I can then split this as J Aj plus Bji, and this here is A transpose, and this here is B transpose, and that ends the proof, right? So that's the proof to why A plus B or transpose is the sum of the transposes together. Now let's look at AB transpose, and I'm saying that this guy is B transpose A transpose. All right, so what this whole thing is saying is that I said this in my video on multiplication of matrices, that if you look at two matrices and you multiply them, this is a compact way of writing all the entries. The Ij component of AB, the product AB, will always be written as this, right? So what I'm going to do is I'm going to try to transpose AB Ij transpose. What would that be? If you follow what we've been doing, this is going to be the same AB, right? Then Ji. Okay. So what this is going to do here is that I'm going to do this with how do I call it? I'm going to do this with this summation I have here. Okay, so I'm so sorry for just pausing there. So if I transpose that, what that's going to give me is if you follow this pattern, I here comes to this I, so it starts from the start, right? And then J will end. So the one that is at the latter end will end. So this guy is going to be the summation as K start from 1 to N. And then this is going to change something here. Notice that in my multiplication video I said that k here is the number of rows in A, and k here is the number of k here is the number of columns in A, and then k here is the number of rows in B, right? So if you have two matrices and you are multiplying them, they should have something in common. The number of columns in A should be the same as the number of rows in B. So k is the number of columns in A, and then k is the number of rows in B. All right. So this is going to be B. Okay. B. Then what do I have here? I'm going to have I'm going to interchange what I have as k and then the rest. Okay. So that's going to give me, let me write it first, kj, and then jk rather. Okay, so jk, I'm interchanging everything rather. So what I'm doing is I'm just interchanging everything. Then a ki. Right, so this is what I have, because I have aik is supposed to interchange to ki, so that I'm going to have the j and then I happening here, bji, right? So if you look at this very carefully, based on this formula, we said that AB, right, ij is the summation k starting from 1 to n, aik, bkj, right, where k is the number of rows and columns in the respective matrices. All right, so this is number of rows in A, this is number of columns in A. I'm so sorry, this is number of rows in B. Now on the other hand, I've been able to write AB transpose as the summation as k started from 1 to n, and then I have bjk, and then aki. Now if I compare this to what I have there, I can say that this is the product of the matrix B and then A. But here, k, the original k, was the number of the number of columns in A. So k in this original one, k is number of columns in A, original A, and then it was the same as number of rows in B, right? But if you look at this is more like k has now become, because bjk is an element in B, k has now become the number of columns in B, and then it has become the number of rows in A, because aki is element in A. So it means we've switched rows and columns in terms of bjk and then aki, and that's exactly what transposition is about. So this is going to be B as the first one, transpose, and then times A transpose, and that ends the proof to why AB transpose is actually B transpose A transpose. I'm so sorry for the delay in here, because I wanted to get all my points and my clarification very right. So that is it. Our next lesson is going to be on trace, and then I'm going to write basic proofs to such properties as well. So you're going to have some properties of trace of a matrix, and I'm going to write a proof to those of them. Thank you, and see you in our next video.